Hello everybody, my name is Luis Esser. Today I'm here to show you how to use chooseGCM. This is most a beginner's guide for those that are not very familiar with R, and to those that are already familiar, I believe it will be very useful to use chooseGCM in your research. Okay, so we will start here in a empty project in our studio. I will open the package. You can install the package directly from R, or you can use a install from DevTools to get it directly from GitHub. Okay, the code is something like that. Yeah. To start, we need to get our GCMs. Okay, and how we do that? We have a function in the package that is WorldClim data. It helps to download GCM data from WorldClim, but you can use actually from any source you like. Okay, so I'll put here WorldClim data. I'll look at the help file to help me. So I'll get this code here. Okay, we have the future. We want the future. We want bioclimatic variables from the year 2090. SSP is 505. Resolution. We want all GCMs. So this function is nice because you can download every GCM available in just one shot. You don't need to know their names or anything like that. You just put that you want all GCMs available and it will return to you. And then we will save it in a new folder that will be called input data and then WorldClim future. Okay, I will run that and it will start downloading. Let's see in my files. It already created the input data, the WorldClim future data, and it's starting to download every GCM for this period. Yeah, so we'll be back in a while. Okay, we are back now with all the data downloaded. We can see that input data folder, we have this WorldClim future folder, and here we have all 23 GCMs available for this SSP, for this resolution and this year. Okay, now we want to bring all this data to R. How we do that? We have here a function in chooseGCM to help import this data. It's called import GCMs. So we use import GCMs. We say which path we have to our data. So it's input data dash WorldClim future. And we have another set of arguments here, parameters here that you can change, but this can be enough. Okay, we can see here that the object S has it's a huge list. Every slot of the list is named after its GCM. So here we have AC, AE, CA. Those are all codes that we used. You can see which is the meaning of each code in the WorldClim data function help file. Here below we have the codes and the GCMs that they represent, okay? And this list will be used in every function from chooseGCM, okay? We can see that every slot is a spat raster object with the same resolution, the same dimensions, the same extent, and the same names for the bioclimatic variables. Of course, we can have multiple other variables here, but in this case we are using only bioclimatic, okay? We have here in every slot has a name that repeats itself. To better visualize data in the end, it's better to have smaller names. So I will change here the names for, I will just exclude this section, okay? So what this function does is it substitutes this piece of text to nothing, okay? So when I run this, I can see now that every slot has just its code as the name. This will be useful in the future when we plot the images, so they stay a little more cleaner, right? Yeah. So what else we need? To every function, I will open here the compare GCMs function file. This function here, I believe, is the most useful for beginners because it summarizes a lot of different statistics that we implemented in the package. We need the object S, which is a list of stacks or general circulation models. And of course, you guys don't need to use import GCMs to do that. Any list with spat rasters that are objects from the Terra package, okay? Any list with these spat rasters will solve. You don't need to use import GCMs. If you are not able to use, if there is something wrong, you can work around with a lapply or something different, or a supply or something like that, okay? But usually when people use the WorldClim data function, it runs smoothly, okay? So we need also not just the object S that we have, but also the variable names that we want to use. I would recommend here to use only variables that are in your models, okay? So if I am using like bio 1, 2, 3, 4 to build my models, I will use only bio 1, 2, 3, 4 to run chooseGCM. As a general example here, I use bio 1 and bio 12, which are mean temperature, mean annual temperature, and annual precipitation, right? So they are both very emblematic variables, and these variables names, they must match the names in the S object, okay? So here we have bio 1, bio 2, I put it here exactly the same as below, okay? In the example here, in the usage, we have bio underscore 1, and this would not work, right? Okay, now we have the object S and we have the variable names. Now what? Now we need the study area. and the study area to run things a little more quickly. We will use some shapefile from the region from Paraná, the Paraná state in Brazil, which the code is something like that. We will use geodata package to download the whole Brazilian shapefile, and then transform that in a simple feature and filter this simple feature into the Paraná state. Okay, I will run this, and then we will select and plot. Let's see. Here is the Paraná state in Brazil, south of Brazil, okay? And we don't need to crop or mask our S object to make it work in the functions, okay? We just need to give this information. So let's see how compare GCMs work. We have compare GCMs, the function. We have to give the list of stacks, that is the S object, the variable names, the var names object, and the study area. Okay? And with that, the package can make its calculations. The first thing it informs us is that the coordinate reference system, let's go back here. The coordinate reference system from S is different from study area. They are not identical. So what the function does is it reprojects the study area to match the GCM's data. Okay, so you don't need to worry with these geoprocessing problems. Okay, let me put here. Okay, now we can see here it's a little messy, but we can work with better resolution now. This is a main function for beginners in chooseGCM, okay? What we see here is three different metrics or algorithms to select general circulation models. The first in the left, the letter A here, is the k-means clustering algorithm. Okay, it builds different clusters, grouping different things together and trying to maximize each of the clusters. In red, we can see which GCMs are being selected by this algorithm. Okay, the same goes in the right here in the hierarchical clustering. Hierarchical clustering is more common in ecology, so ecologists will know it better. We can see also that in red we have the GCMs that are closer to the centroid of each cluster. Okay, these things usually don't match exactly, okay, but sometimes they can perform very similarly. And below here we have our tailor-made algorithm, which is closestdist. Closestdist also selected 3 different GCMs, and you can see that all of them selected 3 GCMs. That's because when we run compare GCMs, we have this argument called k that we can change to any number we like 7, and we can change the number of clusters, the number of GCMs that will be selected by each analysis. Take a look. These are 7 different GCMs, 7 different groups in k-means clustering, 7 different clusters in hierarchical clustering, and 7 different in closestdist. Okay, so this is compare GCMs. With that, we can see, like in the hierarchical clustering, somewhat the relationship between different GCMs. Okay. And of course, we can run each of these analyses, each of these plots we can run in standalone way, like separately, right? In the help page here, we can see that we have these GCMs to run, to know the distance between each GCMs, the correlations, and here the k-means, which will perform this analysis in the left. We have a hclust function to perform the hierarchical clustering, and we have a closestdist function to run this below. Okay. Two other functions that we have that I believe are very useful are MonteCarlo GCMs and env GCMs. These functions perform what we see here below in C and D panels here, the figures. Okay. They work exactly the same as every other function in the package. We have to give some informations, which are the list of stacks, variable names, and the study area. And each of these functions has some differences, right? In MonteCarlo GCMs, we can inform which method we want to analyze. Okay, so here in this plot, what is showed here is the closestdist function, but we can see how the clustering method k-means works. Let's see here. So now I am running the same analysis made here to closestdist, but to k-means clustering. You can see that what this is showing us is that in the red line, the closer the red line goes to 0, the better is the recreation, the synthesis made by GCMs, by groups of GCMs. So if I run k-means clustering and I use 3 GCMs, I will probably have a better result with only 3 GCMs than using 4 GCMs. Let's save this information here so I can show you in GCMs. I will call it k-means MC. Okay, and env GCMs, it's a function to plot the environmental space of GCMs. So here we have 23 GCMs. We can see that this region in yellowish, it has the combinations, the common combinations of bio 12 and bio 1. Okay. In purple we have the hair combinations, like it's probably just one GCM have this combination of bio 12 and bio 1, while these yellow ones have 23 GCMs with this combination of variables. So the aim of our study is to show which is what is the smallest subset of GCMs that can recreate this environment. So we need to focus not on these hair combinations, but the core combination of environments, okay? And we can highlight this function has this argument that is highlight. We can highlight which GCMs we want to highlight here, okay? We can say that is the sum of all GCMs, so we have this image, but we can change the sum to, we have k-means MC here, and this object holds a suggested GCMs. So we saw that with k-means, when we use 3 GCMs, we are closer to the global distance. So I use here the suggested 3 GCMs, and you can see that they are focused on this core region. In purple here we have the shade of this whole environment, okay, and the other colors are each one a different GCM selected by k-means clustering, okay. So here we can say that looking at those at these images, that k-means were able to get really close to the whole environment from using 23 GCMs. So in this case, we don't need to use all 23 GCMs to project our models. We can use only these 3 GCMs, and we will not lose that much confidence, and we will save a lot of time, of course. I will show you finally a function to our tailor-made algorithm, which is closestdist GCM. Closestdist tries to minimize this. Let's go back here to the MonteCarlo permutations. It tries to minimize this red line distance to the blue line, which is, of course, the best case scenario. But when we run MonteCarlo GCMs using closestdist, we have a problem. That is that the red line becomes so close to the 0 that we don't know which is the best one. We can see that in like 19 GCMs it gives a little pop-up, but it is almost aligned, right? So this is not very useful to us. So we have this function closestdist GCMs, which works exactly like every other in the package. We state DS, var names, and study area, and with that we have 1, 2, 3, 4, 5 suggested GCMs. So k equals 5 is the closest one to the blue line here, to 0, right? I will save this information to plot it in GCMs, so we can see how close they are. Close suggested GCMs. Let's see. Oh, here. This is what closestdist have to show to us. Of course, it seems that it's not that good when comparing to k-means, but in our paper, we highlight that in a general use, this tailor-made algorithm is able to recreate the global set of GCMs with very high confidence. So in this way, we are getting to the final thoughts here. I believe that the use of closestdist is very suitable to recreate the global environment of using all GCMs available. The reasoning and the theory behind closestdist and the whole package is in the paper, the article we published in Global Change Biology. We made several tests to see how much time we saved and how far we get from the global mean distances, and with that I believe we can close it. Yeah, for those who using species distribution modeling, running these functions we showed here, we'll have like the suggested GCMs, and then you can download like the whole set of shared socioeconomic pathways and years that you want to project your models. Just changing here the GCM's argument to the suggested GCMs that you are aiming for, okay? And I expect that this package will be very useful to you and your research, okay? Till the next time, bye bye.